Okay, so welcome back. This is part 1B, and we're going to just finish our discussion about entropy and enthalpy and the interplay between them in this chapter. So these are our objectives for this part B. We're going to learn how to predict the signs of entropy. We already know how to predict the signs of enthalpy. We're going to look at standard states, so what that means. What does the standard state mean for enthalpy and entropy? And then we're going to also define this transfer of energy in terms of systems and surroundings. So if we look at entropies, there are some predictions that we can make on how the entropy of a system is going to change. And we already touched on that in part 1A when we looked at state changes. And so remember, we looked at if I go from a solid to a liquid to a gas, that is going to be favored from an entropy standpoint because I'm increasing the movement of those molecules. If I'm going in this direction, now that's going to be unfavored from an entropy standpoint. I can look at the states of something and be able to predict which one is going to have a higher amount of entropy. Factors that affect entropy. So the first one we've already talked about. This is states of matter. And what we know is that a solid has lower entropy than a liquid, which has lower entropy than a gas. So a solid is going to be lower than a liquid, which is going to be lower than a gas. So a gas is always going to have more entropy than a liquid or a solid. So if I have something, let's say H2O liquid going to H2O gas, this is going to be favored. So I'm going to have a change in enthalpy that's going to be positive. It's going to be favored. So remember, a positive sign for entropy means it's going to be favored. This is going to be unfavored from an enthalpy standpoint because I'm going to have to add in energy. So it's unfavored from an enthalpy standpoint. So states of matter. If I'm going from a liquid to a gas, and let's say I had H2O gas to H2O solid, now this would be a scenario where my delta S here is going to be negative and it's unfavored. So I'm going from something that has a lot of movement to something that is very constrained in its movement. This is a solid. But my delta H is going to be negative because to get from here to here, I have to release quite a bit of energy. So this is going to be favored. I can use states of matter to predict my sign. The second one is I can look at molecular weight of a substance. So if I look at molar mass or molecular weight, what you see here is the Nobel gases. So I go from helium all the way to xenon. And what you see here is that my entropy is increasing. So I'm going from 126, and these are always positive. Remember, your entropy values are always going to be positive. Your change can be negative, but your absolute values are positive. So I'm going from 126 all the way up to 169. So not a huge increase in entropy, but it does increase. The trend is that your entropy is going to increase with your molecular weight. If we go back to this slide, I can compare entropy values between a liquid and a gas, and you see that this is significantly greater difference here. So your molecular weight has less of an effect. So state changes is pretty large change in entropy because you're really increasing the movement of these molecules as you go from solid to liquid to gas. So you're going to see a comparable increase in your entropy. Much less of an increase in molecular weights, but still an increase. Our third one would be molecular complexity. So if I have something that's more complex, molecular complexity. So if I just look at maybe carbon monoxide, for instance, and then I compared that to carbon dioxide. Carbon dioxide is going to be a more complex molecule, so I would expect the entropy for that to be greater. Here we have, you can see we're comparing NO, NO2, and N2O4. So as I go down, these are getting more and more complex. And what you see is that my entropy is also increasing. So I go from 200 all the way up to 300. Another way is looking at allotropes. So an allotrope we've already talked about, we just didn't define it as an allotrope. So an allotrope is a substance that's made up of the same molecules. And so when we looked at diamond and graphite, we talked about how diamonds they're more constrained and graphites have much more movement. So graphites are going to have a higher entropy value than diamonds because diamonds have that constriction on the movement. And so that's why diamonds will be spontaneously going to graphite because I'm increasing the entropy there. So an allotrope is two or more compounds that are made up of the same thing. Those would be allotropes to each other. The other thing to look at when I'm increasing the entropy of a system is when I create a solution. So if I think about taking a salt and dissolving it in water, and we talked about there are solvation processes that are endothermic. So if I take potassium nitrate and I drop that in water, it actually, that solution gets colder because it's absorbing heat from the water. And so that solvation, that process of dissolving that ionic compound, is actually endothermic, which means it's unfavored from an enthalpy standpoint, but it still happens. Potassium nitrate is a very soluble compound, and so the driving force behind that, the energetically driving force that makes that spontaneous, is the entropy. Because if you think about it, anytime that you're taking a solid ionic compound that's in this packed lattice with barely any degree of movement, and then I'm dissolving that into water, now those ions that were packed tightly and they only had vibrational movement now can move freely through the water, and so that's going to be always favored from an entropy standpoint. So anytime I make a solution, if I pop my helium balloon in this room, those helium gases are going to diffuse and making a solution of gases that's favored from an entropy standpoint. So the formation of solutions is always going to be favored from an entropy standpoint, may or may not be favored from an enthalpy standpoint. And I can use that to help me predict the sign of entropy. It's going to be different with states of matter. It's going to be larger for gas than a liquid than a solid. It's going to also increase with molar mass. If I compare helium to xenon, xenon's going to have a larger entropy. It's going to differ between allotropes. Whichever allotrope has more degrees of freedom of movement, that's going to have the higher entropy value. If I'm producing a gas, so let's say I have a chemical reaction and I'm decomposing a solid and I'm forming a gas. Now I'm taking that and I'm increasing the number of molecules, and I'm also I'm going from a solid to a gas. So I'm going to have a favorable change in entropy when I have a chemical reaction where I'm producing more gas than I started with. Molecular complexity, and if I take an ionic compound and I dissolve that in water, I'm also increasing the entropy of that system. So let's look at a chemical reaction. So we have molecular weight, we have molecular complexity, allotropes that are going to have different values of entropy depending upon their degrees of movement. Let's look at a chemical reaction. So chemical reactions that produce more gas than reactant are always going to have a change in enthalpy that's favored. A primary one is if I take calcium carbonate, which is chalk, and I allow that to decompose. That's going to form calcium oxide, which is a solid, and it's also going to produce carbon dioxide gas. This is favored from an entropy standpoint for a couple of ways. One is I'm taking one of something and making two of it, so I'm increasing the movement of these molecules just by breaking this apart. So even if both of these were solid, it's still going to be favored from an entropy standpoint. The fact that I'm forming a gas makes it even more favored. If you want to be able to predict on a chemical reaction which one is going to have the greatest change in entropy, you can always compare the number of moles of gases. So this has 1 mole of gas on this side, and this has 0 moles of a gas on this side. So this is going to be favored. My change in entropy is going to be positive. It's going to be favored. If I look at H2 gas plus I2 gas goes to 2HI gas, now my number of moles hasn't changed. I have 2 moles on this side and I have 2 moles on this side. My number of moles hasn't changed, but my complexity here has increased a little bit. So this might be favored. This would be harder to be able to tell if it was favored from an entropy standpoint or not, because I still have 2 moles of gas on this side and I have 2 moles of gas on this side, but my moles of gas on this side are a little bit more molecular complex. So I'd expect this to probably be favored from an entropy standpoint, but it may or may not be a significant amount. However, if I had something like the formation of ammonia, ammonia is formed from 3 moles of hydrogen gas reacting with 1 mole of nitrogen gas. So now if we look at this, I have 4 moles of gas on this side and I have 2 moles of gas on this side. This is going to have a delta S value that's going to be negative, because this is going to be unfavored from an entropy standpoint, because I'm taking something that has more moles of gas and I'm producing something that has less moles of gas. So my change in entropy for this I would expect that value to be negative. All right, let's talk about standard states. And we talked about standard states a little bit in our chapter on solutions when we looked at delta H, enthalpy, and we had this little guy up here. This means standard state. And this allows us to take values from a table. So standard state, I'm going to be able to look up values for my enthalpy based on a set of conditions, physical conditions. So some of my conditions are, for standard state, is if I have a gas, it's at 1 atmosphere or 1 bar. We don't really use bar very much as a unit for gas, but my standard state for gas would be 1 atom or 1 bar. If I had a liquid or a solid, now my standard states would be one that it's pure, a pure substance in its most stable form. And we already do this with our diatomics, so like H2, O2. So if I have oxygen just by itself, its most stable form is as a diatomic. Also, if I have like mercury, that's going to be in the liquid phase because that's its most stable form. So whatever your substance is, whatever its most stable form is, that's going to be its standard state, meaning I don't have to do something to it to get it into this condition that I'm looking at. If I have a solution, then my concentration of that is going to be 1 molarity. So those are my standard states. Anytime I see this, these are the standard states that it's applying to. And so if I have delta H, or if I have H here, and I can say reaction, H for the system, this would be my molar standard enthalpy. The standard is coming from this knot. And I could do the same thing with entropy. This would be my molar standard entropy. Or sometimes you'll see standard first, standard molar entropy, or standard molar enthalpy. All right, so we're going to end part 1b here, and then when we come back with part 2, we'll start doing some calculations with enthalpy and entropy.